Welcome to how to evaluate a double integral by using rectangular or polar coordinates. We will consider Riemann sums for a double integral, and we will write those double integrals for evaluation purposes as integrals, iterated integrals, in either rectangular or polar coordinates. This lesson will cover Riemann sums for defining and approximating the integral from a to b of f of x dx. It will also include MATLAB code for evaluating Riemann sums. We will define double integrals in terms of Riemann sums, and we will evaluate double integrals by using iterated integrals either in rectangular coordinates or in polar coordinates. So let's look at a Riemann sum for the integral from a to b of f of x dx. This Riemann sum can be used to approximate this integral, and a limit of such Riemann sums is actually the definition of this integral. So we start with a number line, and we partition the interval ab. Notice we are integrating from a to b up here. So we'll partition that interval into n equal length subintervals. So right here is a, over here is b. So let's let a be x naught, and then a little bit over x1, x2, out here somewhere x of k minus 1, x of k, further out here x of n minus 1, and then x of n is equal to b. So each of the subintervals here, from one of these marks to the adjacent one, all of these subintervals have the same length. So we have that a is equal to x naught is less than x1 is less than x2, all the way through is less than x of n, which equals b. And then for each k, in other words, for each subinterval up here, pick a number x of k star in the subinterval x of k minus 1 to x of k. So for instance, up here in this diagram, in this subinterval right here, we will pick somewhere in here, doesn't matter where, x of k star. Actually, we could use closed subinterval here. X of k star could also be one of the two endpoints, but somewhere in there, pick x of k star. We do that for each of these subintervals. Then the Riemann sum for the integral from a to b f of x dx using this partition and the x of k stars is, let's call it s sub n. There are going to be n terms in the sum. The sum k goes from 1 to n, f of x of k star times x of k minus x of k minus 1, the length of that kth subinterval. Let's let x of k minus x of k minus 1, let's call that delta x of k. So s sub n then can be written this way. The sum k goes from 1 to n, f of x of k star times delta x sub k. So then the integral from a to b of f of x dx is the limit of these types of Riemann sums that we looked at. The limit as n goes to infinity of the s sub n's, which is the limit of these types of things which are Riemann sums. Now remember that we divided the interval ab into n equal length subintervals. So that means that as n goes to infinity, each of these delta x sub k's is going to just be equal to b minus a divided by n. And so these delta x sub k's all go to 0 in the limit as n goes to infinity. So we're looking at Riemann sums like this, k goes from 1 to n, of this sort of stuff, but we're doing it in such a way that we look at more and more subintervals in the partition of AB. Thousands of subintervals, millions, trillions of these subintervals, and in fact even bigger. The number of subintervals n goes to infinity in this definition of this definite integral. Let's look at an example of computing these types of Riemann sums. Let's look at the integral from 0 to 1 of x squared dx. Let's use a MATLAB program to compute the Riemann sum with n equals 20 subintervals to approximate this integral. And what we'll do is we'll use x sub k star equals the left endpoint, x sub k minus 1, for each of the subintervals. And we'll see what we get for that approximation. Then we'll more finely partition the interval from 0 to 1 into 200 subintervals and see what happens there. Now, from Calculus 1, you hopefully already know that the integral from 0 to 1 of x squared dx by the fundamental theorem of calculus is going to be the antiderivative of this, which is 1/3 x cubed, evaluated at 0 and 1 and subtracted. And when you do that, you'll get that this integral is equal to 1/3, which as a decimal number is about 0.33333. So let's see what happens in MATLAB. Here's one program to find the Riemann sum with n equals 20 subintervals. We clear the workspace, so no variables exist right now. Then we define our sum to be 0. We're going to store the Riemann sum in this variable r sum. For k goes from 1 to 20, we'll let x sub k equals 0 plus k minus 1 times 1/20th. So these x sub k's are going to be the partition of the interval 0 to 1. Delta x in this case is just going to be 1/20th. We're dividing the interval from 0 to 1 into 20 equal length subintervals. Each subinterval has length 1/20th. So our sum then, our Riemann sum, is going to be the previous Riemann sum we computed in this loop here, plus the function x sub k star, which is our integrand here, times the delta x, and then end. So we go through this loop, executing these statements, the body of the loop, 20 times, and each time through the loop we increment our sum by one more term in the Riemann sum. Then after that loop has finished, we will print what the Riemann sum computed up here was. For n equals 20, it turns out that we get a Riemann sum of 0.308750. Well, that's pretty close to the exact value 1/3 of this integral, but it's not too close, I guess, not exceedingly close. But then we only used 20 subintervals here. If we write essentially the same program again for 200 subintervals, what we get is the Riemann sum computed here is 0.330838, and you can see that this number is even closer to 1/3, which is approximately 0.33333. The larger n we use, the closer the Riemann sum should be to the actual value of this integral. This program was written just a little bit more generally. Instead of having for k going from 1 to 200 here, I put a statement in here that capital N, that variable, is set equal to 200, and then we just loop k going from 1 to that value of n, which is 200. And the delta x is also adjusted because we now have n subintervals. The x sub k's are adjusted not by 1/20th anymore, but now 1 over n. And so the body of this loop, this for loop, is executed 200 times. This is a little bit more general and easier to change for different values of n. If you want to see what happens with 300 subintervals, all you'd have to do is change this one line to capital N equals 300. And in that case, hopefully, you would see that we get a Riemann sum that is even closer to 1/3. Let's look at a general definition of the double integral over a region R of f of u and w dA. Let's let R be some region in the two-dimensional plane. For instance, we could let R be the stuff inside what looks like a trapezoid. So R will be a two-dimensional region in the two-dimensional plane. And for a given partition of the plane, we're dividing the plane into each of these little sub elements. We will use only the sub-regions or sub-elements A sub ij that lie entirely in the region R. So for instance, if we look at this little element right here, it's entirely within R, and so that's one of the subregions that we will use in our Riemann sum. This one over here will not be used because just a little piece of it here is not inside R. For each of these little subregions that we have here, let's pick a point which we'll call u sub ij, w sub ij, in that subregion A sub ij. And let's let delta A sub ij be the area of the ijth subregion, A sub ij. We'll form this type of Riemann sum over all of these, I guess you can say, elements colored gold here that are entirely within R. It's going to be the sum over relevant values of I and j of u sub f of u sub I w sub ij times delta of a sub ij. The value of the function at a point inside that subregion times the area of that subregion summed over all of the subregions that are entirely within R. We'll then look at more and more of these Riemann sums where the number of subregions goes off to infinity, and each of these subregions, all of the subregions, have dimensions as n approaches 0. These dimensions, lengths and widths perhaps, all approach 0. And this limit of Riemann sums is the value of the double integral. When we look at a particular problem involving a double integral, we have some choices to make. The shapes we choose for the subregions often will depend on the coordinate system that we use in the problem. That is usually the easiest way to go. If you use rectangular coordinates, for example, the subregions you choose will most likely be rectangular. If you use polar coordinates, the shape of the subregions you decide to use will probably not be rectangles, but a slightly different shape, which we will discuss later. We should choose the coordinate system that makes the integrals easiest to evaluate. So now let's look first at an iterated integral in rectangular coordinates. Let's consider the following problem. Approximate the double integral over R of x squared plus y dA, where R is the interior of the triangle having vertices, if we look over here, vertices 0, 0, which is right here, 4, 4, which is up here, and 4, 0, which is here. We will approximate this integral, this double integral, using a Riemann sum. And we'll get the Riemann sum by partitioning the plane, at least the part of the plane containing that triangle, with horizontal lines like this one, y equals 1, 2, 3, 4, and so forth, and x equals 1, 2, 3, 4, and so forth. Probably we should also mention we have x equals 0 and y equals 0 in our partition. So we want a Riemann sum using this partition. Each of these little subrectangles has area 1. It's a square, a 1 by 1 square. Each subrectangle is a square. So here's what we'll do. To get the Riemann sum, we need to pick a point in each of these sub-regions. I will pick the upper right-hand vertex of each subsquare. So for this first subsquare down here, this vertex is at 2, 1. And so the first term we'll have is going to be our function, this integrand, evaluated at 2, 1, times the area of this subrectangle, this square. And we'll do similarly for all of the other squares that we see here. So we see that x squared plus y is integrand. Each of these subrectangles is actually a square that has area 1. And so we can now set up the Riemann sum. And the Riemann sum is going to be the sum of f, this function up here, the integrand, evaluated at x sub ij, y sub ij. And for the ijth subrectangle, that xy point is going to be the upper right vertex of the square. So evaluate our integrand at that point, and then multiply that by the area of that particular sub-element, the area being delta r sub ij. In this case, all of the sub-rectangles have the same area, so when I and j vary through whatever they vary, this factor is actually going to be the same each time, the area of one of those 1 by 1 squares, which is 1. So if we go through each of these squares and set up this Riemann sum, we'll have f of 2, 1, which is the point right here, times the area of that square, 1, plus f of 3, 1, which is this point right here, times the area of this square, which is 1, times f of 4, 1, which is the point that we see right here, times the area of this rectangle. And then going up to here, we use this point, which is 3, 2, and then this point here is going to be 4, 2, and then for this rectangle, the upper right-hand vertex is what? 4, 3. And so we plug all those in. Using the fact that f of xy is x squared plus y, f of 2, 1 is 2 squared plus 1, which is 5. Multiplied by 1, it's still 5. Similarly, f of 3, 1 times 1 is 10. F of 4, 1 times 1 is 17. F of 3, 2 times 1 is 11. F of 4, 2 times 1 is 18. F of 4, 3 times 1 is 19. And if you add all of these together, you get 80, which happens to be, if you write it in terms of thirds, 80 is 240 thirds. Why am I interested in this? Well, for comparison, actually. The exact value of this integral over this triangle is 224 thirds. Our approximation was 240 thirds. Fairly close, but not too close. Later, we'll see how to compute this type of integral exactly using Fubini's theorem and the fundamental theorem of calculus. That we will see shortly. Let's look at a version of Fubini's theorem for evaluating the following double integral. The double integral over a region R of a function w of x and y dA. So here's the picture. We have a horizontal x-axis, a vertical y-axis, and the region R is defined the following way. R is a set of xy such that x is between a and b, and y is between f of x and g of x. In this picture then, here is the vertical line, x equals a. here's the vertical line x equals b. This lower curve is y equals f of x. This upper curve is y equals g of x. So how do we evaluate this double integral? We do it as an iterated integral. The double integral over r of w of x, y, dA is the following. It's the integral from x equals a to b of the integral where y goes from f of x to g of x, w of xy, dy, dx. This is an important formula, and it holds for any function w which is continuous on this region R that we're integrating upon. And this can be used, this formula is in rectangular coordinates, and remember double integrals came from Riemann sums, and we'll find out that integrals in polar coordinates can also be thought of as Riemann sums, and the same formula will be used more or less in polar coordinates too. But the problem is in polar coordinates, the little area elements that we have, the subregions, are not going to be rectangles, they'll be something else. And so because of that, we don't just have a dr d theta here, we'll have something slightly different, a slight modification, which we can see how it occurs when we get to that. But right now, we can think of this as just a problem using rectangular coordinates, integrate a function over this region R by using this formula. So let's look at an example of changing a double integral to an iterated integral and then evaluating that iterated integral. So let's look at the integral over a region R of x squared plus y dA. That's the one we just looked at with Riemann sum approximations. And so here is the region R, again, same triangle as before. This side, the hypotenuse, goes from 0, 0 to 4, 4. So the equation of this curve right here is y equals x. And so let's see what we can do with this. If you look at this picture for a minute, x goes from 0 to 4, and so the outer integral is the integral where x goes from 0 to 4. And now, what about the lower and upper curves? The lower curve right here is y equals 0, part of the x-axis, and this upper curve for the region R is y equals x. And so the inside integral is going from y equals 0 to x. Then we have the integrand x squared plus y dy dx. So we want to evaluate this. The way to do it is to start with this innermost integral and integrate with respect to y, keeping x fixed, more or less like a constant. And then after this inside integral has been evaluated, it will be just a function of x. And we'll integrate that with respect to x using these limits of integration. So let's see how that goes. So we have the integral on the outside, x goes from 0 to 4. Now, using the fundamental theorem of calculus for this integral with respect to y, if we anti-differentiate x squared with respect to y, that's just x squared y. The integral of a constant with respect to y is just that constant times y, and x squared here is playing the role of a constant factor. The integral, the antiderivative of y dy is 1/2 y squared. And then we're going to evaluate this by substituting in y equals 0, also y equals x, and subtracting. When we do that, this part simplifies to just x cubed plus 1/2 x squared. Let's see, can we see that from up here? If we substitute y equals 0 in here, this term is 0 because it has a factor of y. This term is also 0 because it has a factor of y. So it's 0. When we substitute x in, we'll get x squared times x, which is x cubed, plus 1/2 x squared, which is what we have here. And we're now integrating that with respect to x going from 0 to 4 in this definite integral. And now this definite integral is easy to evaluate by the fundamental theorem of calculus. We have an antiderivative of this function of x is what? Antiderivative of x cubed is 1/4 x to the 4th. An antiderivative of 1/2 x squared is 1/6 x cubed. And by the fundamental theorem of calculus, we evaluate this antiderivative at x equals 0 and at x equals 4, and then subtract those two values that we get. And what we get, you can check this in your spare time if you want, is 64 plus 64/6, and that simplifies to 224 over 3. We will now consider how to convert a double integral to an iterated integral if we're looking at a problem that involves polar coordinates. Here is a graphical summary of polar coordinates in a nutshell. Suppose we draw a straight line to start with, and we'll call that the polar axis. Then we can create an angle theta and draw another line here which makes that angle theta with the polar axis. We have a point out here, and we want to define the polar coordinates r, theta. Well, the first coordinate r is the distance from the pole, which is right here, more or less like the origin of a coordinate system, out to that point. Theta is this angle. So basically what we have here is a distance r and an angle theta, the direction where we go to find our point. Now, one thing to point out here is that r can be positive or negative. If r is negative, we would go out in this other direction instead of in this, the positive direction. Also, theta can be a positive or negative angle measured in radians. If it's a positive angle, we will start at the polar axis and go counterclockwise to measure that angle, which will then give us the direction for the point we're seeking. If theta is a negative number, we will go clockwise from the polar axis down this way. So r can be positive, negative, or 0, and theta can also be positive or negative or 0. So to set up polar coordinates, all you need is a unit of length, a polar axis, and some way to measure or construct angles. Often we want to compare polar coordinates with rectangular coordinates. In that case, the most common thing that people do is to let the positive x-axis be in the same direction as the polar axis, and in fact on top of the polar axis, and the y-axis is perpendicular to that x-axis. The point, which is the origin of our coordinates x and y, this point in polar coordinates language is called the pole. So in polar coordinates, we have a point here called the pole, we have a polar axis, and we have another line or ray going out to the particle that we're interested in, and we know the direction of that ray by specification of this angle theta. In this setup, there are relationships between the coordinates r and theta in polar coordinates and the rectangular coordinates x and y. They are given over here. First of all, by looking at this right triangle, we drop a perpendicular down from the point r theta to the x-axis, and let this distance be y, let this distance be x, and let this distance be r. And we notice that we have a right triangle here with hypotenuse r. From this, we can see that x has to equal r cosine theta, and y has to equal r sine theta. Also, using the Pythagorean theorem, we can see that this r distance, the hypotenuse distance squared, is equal to x squared plus y squared. And so we can write that r equals plus or minus the square root of x squared plus y squared. Also, by looking at this right triangle with angle theta here, the tangent of theta is going to be y over x. So theta has to be the inverse tangent of y over x. Now coming back to this plus or minus here, we mentioned earlier that r can be a positive number or a negative number. So in the situation that you're looking at, you have to figure out what polar coordinates you're using for the point x, y, and choose the sign correctly. Here is an example of what we can call polar graph paper, a piece of paper for graphing curves that are expressed in polar coordinates. Right at the center of this polar graph paper is the origin. From the origin, we have lines radiating outward, I guess maybe rays radiating outward. For instance, the ray coming down this way is theta equals 0. All the points on this ray have a theta coordinate of 0. On this ray, all of the points have a theta value, theta coordinate of pi over 8. For this one, pi over 4. For this one, 3 pi over 8. For this one, pi over 2. And we could continue on over this and actually continue further and further and further, getting values of theta that are larger than 2 pi. Or we could start at theta equals 0 and go in the opposite direction for negative values of theta. We also see some concentric circles here. At the pole, more or less the origin here, r is equal to 0. If you count out, you'll find that there are 1, 2, 3, 4, 5, 6 circles here. And I also have some rectangular coordinates here for length shown. And if you compare the two, you'll see that this outmost circle has a radius of 3. So all of the points on this circle have an r coordinate of 3. The next one in, the r coordinates of these points are all 2.5. For the next one, 2, 1.5, and 1. And finally, this one right here, 0.5. So what kind of area element are we going to use in polar coordinates? Let's consider this picture. Right here is the pole, and we have two concentric circles with that pole as the center. This one has the equation r equals r sub j minus 1. This outer circle, r equals r sub j. We have two rays coming out, theta equals theta sub k minus 1, and theta equals theta sub k. There's a region between those two circles and those two rays, colored in, I guess, blue here. What is the area of this blue subregion? Well, we can start by saying the area of that subregion, which I'll call A sub jk, is equal to the area of the ring all the way around times the fraction of the ring that you just have by going from theta sub k minus 1 to theta sub k. So let's see. The area of the ring is pi times r sub j squared minus r sub j minus 1 squared, just taking the area inside this larger circle minus the area inside this smaller circle. And then, remembering that theta is measured in radians, the fraction that we have of that entire ring, but just going from theta sub k minus 1 to theta sub k, is theta sub k minus theta sub k minus 1 divided by 2 pi. So now what we can do is write this difference of two squares as the sum of the two numbers times the difference of the two numbers with that pi outside, and we'll just leave this fraction the way that it is for the time being. And then let's take out this pi from this denominator. Let's put it out here, dividing this pi by pi. This 2 in the denominator we will put in the denominator of a fraction having this as the numerator. And so that area of this small object there, that sub-region, is pi over pi times this factor times this factor times this factor. Now, if you look at this factor, well, first pi over pi is 1. Now, let's look at this factor. It's just the average of r sub j and r sub j minus 1. Why don't we call that r sub j star? So we have 1, and this is r sub j star. This difference in the r values we'll call delta r sub j. This difference in the theta values we'll call delta theta sub k. So then when we look at differentials, we can look at this as giving us dA is r times dr times d theta. So let's look at the Riemann sums for the double integral in polar coordinates. First of all, we can say that for a given partition, the Riemann sum will be the sum over all relevant j and k of f of r sub j theta sub k times delta a sub jk. But we just saw what delta of a sub jk was. So we substitute that in. And so we get the Riemann sum is the sum over all relevant j's and k's, the function evaluated at r sub j theta sub k, and then this area is r sub j star times delta r sub j times delta theta sub k. So this kind of gives us a very big hint as to what the double integral is going to look like, the iterated integral. It's going to be an iterated integral over f of rj times r dr d theta. So now let's see how we can evaluate one of these double integrals in terms of iterated integrals, an integral of an integral. Suppose the region R in polar coordinates is the set of points whose coordinates are r theta, where theta is between alpha and beta, and r then, for each theta, r is between g of theta and h of theta. Picture looks like this. Here's the curve r equals h of theta, down here r equals g of theta, and two lines theta equals alpha and theta equals beta. So r is this colored region in here. Then the double integral over r of a function f of r theta dA can be evaluated in polar coordinates by this iterated integral. The integral where theta goes from alpha to beta of the integral where r goes from g of theta to h of theta, our integrand f of r theta and then the dA is replaced by r dr d theta. So let's consider a problem involving integration using polar coordinates. Let's evaluate the double integral over a region D of x squared dA, where D is the region shown over here on our graph over here. If you look at this region is bounded by this circle, r equals 3, and this circle out here, which is r equals 6, and two rays coming out from the pole. Theta equals pi over 8, theta equals pi over 4. Okay, so this is the region that we're going to be integrating over. So then our solution, the double integral over d of x squared dA, is going to be what? Well, theta goes from pi over 8 to pi over 4, and then for each value of theta in that range, r goes from 3 to 6. So the inner integral, r equals 3 to 6. X, remember, in polar coordinates is r cosine theta, so x squared is r cosine theta quantity squared. The dA is replaced by r dr d theta. So what happens to that? Well, let's see what we have here. We have an r squared here times another r, so that gives us an r cubed. And we also have a cosine of theta quantity squared here, so cosine square theta, and then dr d theta, and the limits on the integral did not change at all. If we look at this, we notice that this r in this dA differential was combined with the factors of r that we had here. So our integrand in this integral is r cubed times cosine square theta, and it's integrated with respect to r and theta. So what we do is we start with this inside integral, evaluate that integral with respect to r using the fundamental theorem of calculus, and whatever we get there, we're going to then integrate that with respect to theta. So here's what we're going to get. This is an integrand that factors into a function only of r times a function only of theta. So this could be written as the integral of r squared dr times this integral of cosine squared theta d theta, which is what we did here. The integral of r cubed dr is 1/4 r to the 4th, and we're evaluating that at 6 and 3 and subtracting. So that explains this factor right here. And when we integrate cosine square theta d theta, where theta goes from pi over 8 to pi over 4, this is the antiderivative of cosine square theta. You probably evaluated this type of integral of cosine square theta d theta before when you talked about techniques of integration. And so we're going to plug in pi over 8 and pi over 4 for the theta here. Notice that here we have a theta, here we have a sine of 2 theta, so have to be aware of that. So now we plug in those numbers, do a little bit of arithmetic to get our final answer, the value of that integral. This integral was pretty easy to do. The limits of integration were all constants. R went from 3 to 6, theta went from pi over 8 to pi over 4. That turned out because the boundary of this region D consisted of parts of concentric circles centered at the pole or origin, and the other two sides of D turned out to be very easy to describe in terms of theta. So this problem was really set up for an integration by polar coordinates. We could do this integrating with rectangular coordinates, but then the integral would be much harder because we'd have different limits of integration for x and y rather than what we had for r and theta. So pick the coordinate system that makes things easy. So let's look at a previous problem that we considered. The integral over a region R of x squared plus y dA. Here are my x and y axes. R is this triangle, this right triangle, where this is the origin for that vertex. X equals 4 has this other vertex, and this vertex is at the point 4, 4. What we're going to do is to evaluate this integral again. But now, instead of using rectangular coordinates, we're going to do something kind of idiotic. We're going to integrate using polar coordinates. We'll take this double integral, which has a particular value, and it's the same value whether you use polar coordinates or rectangular coordinates or any other coordinates, but we'll try to evaluate it using polar coordinates. And we'll find that it's very messy to do that way, and to save a little bit of time and to see that we actually do get the same answer we got before, we're going to, at some stages in this calculation, rely on SageMath to do some of the, I guess you can say, dirty work, evaluation of messy expressions. So what we'll conclude from this example, I guess, is that if you're going to look at this triangle as the region, the interior of the triangle as this region, it doesn't involve parts of circles, and it does have one ray. Y equals x is the ray theta equals pi over 4. But in general, this doesn't really mesh very well with polar coordinates. So let's see what happens. Okay, so let's evaluate the double integral over R, over that triangle that we can see here, of x squared plus y dA. Now, this side was y equals x, which is the same as theta equals pi over 4. This side was x equals 4, and that's the same as r cosine theta equals 4. So we can write this the following way. X squared plus y is going to be r cosine theta squared plus r sine theta. The dA is going to be r dr d theta. And then the limits are going to be the following. For r on the inside, r is going to go from 0 out to this side right here, and for this vertical side, r is equal to 4 divided by cosine theta. Just divide both sides of this equation by cosine theta to get this upper limit here. And for theta, we're going to go from theta equals 0 up to pi over 4. So this is the integral that we have at this stage. Just do a little bit of algebra here, multiply by this factor of r, and we can write the integrand this way, dr d theta. And then we can integrate this inside one with respect to r. For instance, the integral antiderivative of r cubed is 1/4 r to the 4th. It's multiplied by cosine square theta. And the integral with respect to r of the second term is 1/3 r cubed sine theta. And we're evaluating, using the fundamental theorem of calculus, r at 0 and 4 cosine theta. And then whatever that is, we're going to integrate that with respect to theta, and it turns out that we get 224 over thirds. but let's forget this part for 1 second. If we plug in these two values into this expression and subtract, we get this stuff right here, and that's fairly complicated, but we want to integrate this with respect to theta going from 0 to pi over 4. So we do that integral. It turns out to be this stuff as far as antiderivatives go. Using the fundamental theorem of calculus, we'll plug in theta equals 0 and pi over 4, and we get 224 thirds. So this turned out to be very messy in a way if we did all of these calculations in detail. This anti-differentiation going from here to here is pretty simple, but going from here down to here, finding that antiderivative would take quite a bit of work, most likely. We can evaluate this double integral that we have been looking at with one command. Notice that we need variables r and theta, so we'll declare r and theta to be variables. And now we're going to look at the value of the iterated integral. First, I'm going to assume that theta is less than pi over 2, and I'm also going to assume that r is greater than or equal to 0. Then the iterated integral that we're going to look at is the integral of r squared of r times cosine theta, quantity squared, plus r times theta, all that times r. And we're going to integrate the inside with respect to r, going from 0 to 4 over cosine theta. And the outside integral will be integrating with respect to theta, going from 0 to pi over 4. So if we do that, if we execute that statement, let's try that again. Now we want to simplify that, and it turns out to be 224 over 3. Now, next thing we're going to do is piece by piece. Well, another method of evaluating this iterated integral. We'll evaluate the inner integral as far as just an inner antiderivative goes first, and then we'll use the fundamental theorem of calculus to get the value of that inner definite integral. So we'll start by the evaluation of the inner integral, and we did it right here. Inner integral of r is the integral of all of that stuff integrated with respect to r, and then we show the value of it, which turns out to be 1/4 r to the 4th cosine theta squared plus 1/3 r cubed times sine of theta. Next thing I want to do is to evaluate that antiderivative, this inner integral, at 4 over cosine theta minus that inside integral evaluated, that antiderivative evaluated at 0. Here we're using the fundamental theorem of calculus to calculate that definite integral on the inside. And it turns out to be all of this stuff. 64 divided by cosine theta squared plus 64 thirds, sine of theta divided by cosine of theta cubed. Let's simplify that and see what we get. Well, didn't simplify too much, did it? So we have this as the value of that inner definite integral. Now we need to evaluate this by integrating it from theta equals 0 to, I believe it was pi over 4. So first of all, let's calculate the outer integral as a function of theta. And so we'll execute that. We can also show that in a more mathematical form. And so we get that outer integral as an antiderivative of the inner integral is this stuff, 32 over 3 cosine theta. This is cosine of theta, quantity squared, plus 64 times tangent of theta. To evaluate that outer definite integral that we're really interested in, we'll take this outer int at pi over 4 minus outer int at 0, And when we do that, we get that the answer is 224 divided by 3. The same answer that we got up here by evaluating the iterated integral in one cell as the integral of the integral. In this video, we considered examples involving the integral over a triangular region of x squared plus y dA. And the triangular region R, in this case, was this triangle. It's a right triangle with base equal to 4 and the height also equal to 4. We saw that when we wrote this as an iterated integral in terms of rectangular coordinates, the iterated integral turned out to be this. When we evaluated it, that gave us 224 thirds. So the value of this double integral by that calculation was 224 thirds. We also looked at this same double integral in polar coordinates. When we changed it, the double integral, into an iterated integral in this case, we got this more complicated integral. The integral from theta equals 0 to pi over 4, r equals 0 to 4 over cosine theta, and this stuff. The quantity r cosine theta quantity squared plus r sine theta times r dr d theta. And evaluating this was, well, took a long time if you're doing it by hand, lots of calculations to do. And in the end, we found out that the value of this iterated integral also was 224 thirds, the same as we have up here. So the value of this double integral, and any double integral for that matter, is not affected by the coordinate system you choose in order to evaluate it. This double integral has an intrinsic value, unchanging. Thank you for watching this video. I hope you have found it to be an enjoyable learning experience. You might also enjoy some of the other videos I produced dealing with topics in ordinary differential equations and calculus. Have a nice day.